All right. Hello, everyone. Welcome to today's presentation on the geologic history of the Nebraska Sand Hills. My name is Samantha Gentry, and I'm an AmeriCorps member serving with Conservation Nebraska's Common Ground program. Conservation Nebraska's mission is to protect our state's natural legacy by educating the public, supporting communities, and increasing civic engagement, which we accomplish through locally led education efforts and community engagement projects to address conservation concerns like this event today. Before the presentation, there are a few housekeeping things to go over. For those online, your cameras will remain off and you will be muted throughout the presentation. Please type any questions you have into the chat or the Q&A section, and we will answer those at the end of the presentation. For those in person, please feel free to raise your hand when you have a question. Some questions may have to wait until the end of the presentation due to time constraints. This presentation will be recorded and will be uploaded to Conservation Nebraska's YouTube page within the next couple of weeks. So if you miss any part of today's presentation or would like to revisit any part or share it with others, you will be able to find it there. Following the presentation, we will have a very brief survey that should only take less than a minute to complete, both online and in person. The survey helps programming like this one, so we appreciate you taking the time to fill those out. If anyone in attendance is interested in speaking with the Conservation Nebraska member regarding conservation issues in Nebraska, or to find out more about what we do, please contact us at info@neconserve.org. I would like to introduce Dr. David Loope from UNL, who is going to speak to us about the geologic history of the Nebraska Sand Hills. Dr. Loope, a native of rural Virginia, taught geology at UNL from 1981 to 2018. He majored in biology at Duke University from 1967 to 1971, but fell in love with geology during his 3 years of work with the National Park Service at Canyonlands National Park in southeast Utah. He earned a second BS in geology at Utah State University and completed his PhD at the University of Wyoming. He and his wife live in Lincoln. She actually works at Morrill Hall. Their 2 sons now live in Flagstaff, Arizona, and Blacksburg, Virginia. Please join me in welcoming Dr. Loope.
Thanks for coming today. Nice outside. But good to see you here. I really love Nebraska, and prior to 1981, all I'd seen was the highway going across from Virginia to Wyoming to Utah, etc. If you were in a car, right here, you're facing this way. What direction is that? North. North is a good answer, and it's not exactly to the north. But these dunes are, well, these are sand dunes, these big ridges, as I think you know, they're windblown sand dunes. And they were, the sand was transported by winds out of the north dominantly. Yes, there were some counter winds, but winds out of the north were the main thing. And so he knew, because those are the steepest slopes. If you were going south, you would have gone up, and then you'd be cutting through a steep landscape. That's the downwind part of the sand dune. Not working. There. Okay, this is a slightly different perspective. This is from, what did I say? I in space looking down. How many of you have used Google Earth to see the sand dunes? Okay, I tell you, that was just a wonderful experience the first time I saw that. So these are giant landforms, and I'd say some of them are 5 miles long. This is 2 miles. Well, yeah, that's not an overstatement. They're elongated, mainly east-west. And so some of the highways, you go up and down and up and down. But on Highway 2, you don't really get much variety. So these are some of the basic things and some conclusions already. So where do dunes form? They form in places where plants are either non-existent or sparse. And that's because the wind can't move through vegetation very fast. And so plants can really hold down the land surface and prevent any erosion and migration. So where would you go? Deserts or beaches? Those conditions are important, and we'll talk about. There's no desert there now. Today, is there? It looks like Ireland out there. But clearly, to make dunes like that, it had to be a desert. There weren't any beaches. The sea has come and gone many times in Nebraska's history, but no, these are much younger than any of those marine transgressions. So dunes on the Great Plains presently stabilized by prairie grasses. Where'd all this stuff come from to build these giant ridges? It's not like they got pushed up from below. They had to be delivered. The sand in the dunes came from the Rocky Mountains. And there's clear evidence that it came from billion-year-old granites that are dominant. If you take 80 and out of Nebraska into Wyoming and into Wyoming, you start seeing these big masses of granite, and that was broken down, weathered, and then, as you know, the landscape is up on the west and down to the east. The plains, rivers carried sand, silt, and gravel, even some big cobbles, got them out of Wyoming and then left the gravel and the boulders behind. But the sand and the silt kept coming this way. And the rivers dried up. That's a necessity. So that can happen in a desert. And so winds from the north drove the sand and the silt southward. What is silt? I'll define it the next slide. So the giant dunes were built in a desert climate, and it was during the Ice Age. And none of the dunes that are out there today are that old. And I'll be emphasizing that the dunes move like a tank tread and are being reborn as they migrated along. So you can't find any dunes that are older than 18,000 years, I think. All right. The last time there was significant amount of wind driving sand on the dune surfaces, that was between 800 and 1,200 years ago. And I'll show you the evidence for these conclusions. So there's several different kinds of dunes in the dune field, but I'll be talking almost exclusively on the transverse dunes, the ones in yellow. And I want to tell you about loess, or explain what loess is. And there it is, sand or grains from 1/16 of a millimeter to 2 millimeters in diameter. The ones in the dunes here are smaller than that. 1/8 of a millimeter would be the average size. So this is pretty fine sand. And the silt is, of course, much finer. And clay, basically non-existent. So the they're made of very fine or fine sands, and the loess is composed nearly 100% of silt grains. And the key thing there is grinding of the larger particles into silt-sized grains by the movement of glaciers. And the loess is an important part of this whole situation. All right, so the wind's coming from the left, going to the right. The sand moves by the process of saltation. Salto, I think, is Latin for jump. And so the wind is able to get them moving. And once they're up in the air, they really zoom along and hit with considerable energy. And that ejects another sand grain or two. If there's gravel out there, it will make the gravel creep along. And an important thing here is this stuff. That's the silt. So the sand grains are zooming along, but they don't move more than a few meters before they're back down and then move a similar distance the next time a wind gust comes. But the suspended silt gets up into a big cloud, dust storm, and it can go great distances. And I was showing you the big map again, and it'll show where the sand is and where the silt is. And the silt is downwind from the sand. The sand stopped moving because it reached a river. And the saltating grains can't make it. But the dust, the silt here has no problem getting across. And so the loess, you got the sand and the loess almost touching one another with a river in between. Yeah, and so the suspended material falls onto the desert multiple times, but it gets thrown back up multiple times. And then eventually, and maybe it's right at a river, it'll fall into vegetation, and then there it is. It's not going anywhere now. So that's the two kinds of wind moved sediments and what's happened in Nebraska. Here's a dust storm, and the best photo I could get was from Australia. But there's the turbulence, then the suspension. So these grains are so small, it can't fall. There's too much friction. There's a lot of surface area, not much mass in a silt grain. So it can't fall very fast at all. Eventually, when the wind dies down, it does fall, of course. All right. I want to talk a little bit about hydrology too. I know this is geologic history, but the water is a big part of the story of the Sand Hills, especially today. And so there's a cartoon of sand grains, and water has entered from above. And you can see that there's a little bit of water here. That's capillary action. But most of the water, let's say from a thunderstorm, is moving vertically downward and filling the pore spaces. And that's the water table right there. The grasses can get their roots easily to this water. And cottonwood trees can get their roots down to this level. In the loess, you got a similar thing. I just brought this down to size here. But so if I had a jar in left hand and a jar in my right hand, one has marbles and one has BBs, and they all are to the brim with water. Which one has the most water? It's same, which is kind of surprising. So that's porosity, but permeability is probably more important than the porosity. The permeability is how fast can the water move. So as I said, west to east slope, the groundwater is moving eastward, and it can move through this stuff much faster than it moves through this. So 80% of the water in the Ogallala Aquifer is beneath the sand hills. It's there because you get a big thunderstorm and water is pouring down on the land surface, but the water can move down and none of it usually runs off. Whereas this stuff, you could get a flash flood, and they get flash flood south and east of the sandhills pretty often. Okay. So here's the steep downwind surface. There are some cuts here formed by runoff, but you know, they may be 100 years old. You know, and one event can make a scar like that, and that's that. And maybe if a rancher is close by, maybe you'll get a flood coming down, and all right, that's really rare. But guess what? The water is still not going to leave the scene very far. It's still going to become part of the groundwater as it moved off to the right, maybe a couple hundred or 1,000 meters. But it's recharging the groundwater. And that's the key thing on the Ogallala Aquifer. It's this huge vat with water that's moving very slowly. And it's gobbling up all the water that falls out of the sky. And all right, here, the loess is here. Notice kind of a different pattern here of the streams and rivers here than here. That's because there's very little runoff to rivers in the sandhills. So nearly all the rain and snow is being captured here. A lot of this is lost to runoff, and that's a problem rather than, you know, rather than a good thing. And so there's Columbus, and there's where the Loope rivers meet the Platte. And here's another view of it. The key thing here is that the Platte can dry up late in the summer, but not the Loope River. These are among the most steady flowing rivers in the world. And it's because of that sand just taking up the water and storing it and letting it go slow. Okay, so here we are in Lincoln, and we're lucky. We've got a water system, and we're lucky that there was a sand hills here, and that provides water year round without stumbling in late summer. I didn't mention ripples. So probably if you spend any time on the beach, you've seen these wind ripples, and they're made by the saltating grains. And back here is the avalanche slope. So this is an active dune field, obviously, and you don't see any gullies in this. This is smooth, and the avalanches are the material that slowly moves up the backside, and then then the wind takes it over the crest, and it makes a lump on the steep downhill face, and it gets steep enough, it comes avalanching down. And so that's how dunes move, is avalanche by avalanche by avalanche, and they're fed by these ripples that are moving up. So here are the steeper south facing surfaces, and here are the low slopes. There's a lot more vegetation here than here, and that's just due to breaking up, well, and the cow tracks going along the steep sides. It's kind of a mess. So much better habitat for grass on the back side of the dunes. Okay, so there's Highway 2 and here's 61. All right. I mentioned a tank tread. So here's the wind blowing this way. There's the steep side. Avalanching takes place here. And what you have in cross section, which is rarely exposed, but you'll have the chance to see it in a few slides coming up. These big dunes and small dunes too have not flat surfaces you'd expect. The sediment comes to rest out on a smooth, flat surface. No, this stuff comes to rest on a steep surface like that. And that is, if you were to dig into the dune, you could see if it's a really ancient dune, you got to question what direction was the wind moving. Well, you can tell. All right. So these dunes, and we're interested in the history. That was part of the show, the geologic history of the Sand Hills. So suppose you wanted to know when this dune when the dunes were last moving. And that question is answered here. If you can date these materials, you've got the answer to how far back do you have to go to get the desert, and in this case, 800 years. Now, I'm not going to show you how we got that date right now, and I won't tell you much about how we did it. It's kind of a black box thing, but there is this amazing lab technique to, if you keep the sand grains in the dark, you go in with say, an aluminum tube and you push it into the sand and then carefully pull it out. Don't let it see the light. Take it to a dark laboratory and they'll expose it to a blast of light. It will give off energy of a certain amount. The longer it's been in the dark, the more energy it has to give away. And that technique was found maybe after I'd been here 10 years. So first 10 years I was here, how are we going to get any ages on these dunes? Carbon dating, you've probably heard of that, but not many logs in the Sandhill dunes. All right, so how old are the dunes? And that's a tough question. Are you talking about the dune field? Or are you talking about that dune right there? So that dune right there, you can go to this place. This cross bed is older than those cross beds. And the erosion has moved all the stuff that was back here. So we found some dunes with the trailing portion of them given a date of 18,000 years. So that's back into the Ice Age. Let's see. All right. Now, when I went to University of Wyoming, I didn't study the Sand Hills. I went back to Canyonlands National Park and I was working on rocks like this. And it was argued that they were deposited in below sea level because they had tiny little fossils in them, marine fossils. And wait a minute, the book says, that if you're trying to figure things out, this seems to have all the characteristics of a windblown deposit. And you can see the avalanches pretty clearly here. The wind ripples deposited this, and so the dunes were much larger than the preserved cross beds. The dune went way up here, and this is an erosion surface that it cut it away. And later another dune came in over, giant dune, maybe a couple 100 feet high, and it was cut off as well. So this was 200 million years ago. And here's a person for scale. Will the sand hills eventually become a thick sandstone? This was all sand at one time, 200 million years ago. I think the answer is no. And why do I think that? Well, another place, Zion National Park in southwest corner of Utah. There's 2,000 feet of nothing but crossbeds. Dune after dune after dune after dune after dune. What, you made a mountain out on the desert floor? You made a 2,000-foot high mountain? Not likely. And the higher you get in the atmosphere, the faster the wind is blowing. There's a certain limit to how big dunes can get. And I don't know that number, but I would say the dunes in the sandhills are pretty close to that limit. So what process could have allowed this to happen? That word right there, subsidence. All right, you don't have to build a mountain of sand. You can have the land surface going down, down, down. So you have heard of plate tectonics, and usually you think up, up, up. That's how you make mountains. It goes down, down, down too. And Zion was right kind of at the edge of the North American craton, the slab of continental rocks, and it had been stretched, and an ocean had been opened, and it was thinned by that, and it sunk down, and 100, 200, 300, 2,000 feet of sand here, whereas back at Grand Canyon, it might be only 200 feet. So preserving these rocks, I mean, I think you know that we know a lot about Earth history, but there's so much that's missing in the sedimentary rock record. You've got to have subsidence or you don't preserve anything. And that's why I said, I don't think our sand hills are gonna ever make it to this stage. Okay, arid crossbeds. This is the best place. This was Calamus River Dam site, 1981, my first trip to the sand hills. This guy wanted to show me some of the best places, and he sure did. And one of the students that came with us, I'm going along and I'm showing Bob and the students all the little, these are thin little layers, and they're made by wind ripples. And I was going into detail. This fresh new professor's going to tell you what he knows if you're on the field trip, and let's go to the next place that he knows something about, and the next. And this one kid's, what is that? What's going on there? I'm not sure. Might have been messed up by the mechanics of forming the cut. But I took a photo of it and scratched my head for a while, and I think we ought to go back there and look around. And so what's that? It looks as if there's these thin layers deposited by wind ripples, and something crushed it. Something that's got two toes, maybe a bison. So that's the best cross section I've got, but there's a lot that are preserved like this. So these animals were walking on bare sand, and they were heavy, so they pushed it down. And so there's evidence for sort of an in-between thing. The dunes are actively migrating, but there's these big animals that are eating something, and it must be grasses or other vegetation between the dunes. And we came back and dated this, got some sand and kept it in the dark. And that came back at about 800 years ago. We know that from OSF. Okay, so what did the sand hills look like when the dunes were active? I kind of like this. These dunes aren't as big as the ones in the sand hills, but they're active today and they're north of Rock Springs, Wyoming. And you can see there's some big animals out there, and actually they have the split the two toes. And so I've spent some time out there looking for digging into those dunes and looking what the cows have done. But yeah, you need to have enough rainfall and a cool enough temperature that you don't evaporate at all to get these big mammals. And so my guess is that 800 years ago, Nebraska looked a lot like this with bison instead of cows. We found one track that was quite large, and notice that it's in flat-lying sediment, I think deposited by a stream, a small river. And so flat beds, and it's either a mammoth or a mastodon. And that means it has to be at least 10,000 years old. They died out about that time. Go back to Utah with your knowledge of all these tracks, and that's what these are. Nobody had seen these. Trackways had been found. So here's a track, here's a track, here's a track, and you're looking at a flat surface, a single bed. And so you see a trackway, but nobody had picked up on the fact that a lot of the bedding is messed up. And look closer, that's really tracks of animals walking on dunes. And some of them were dinosaurs. So this is 200 million year old Jurassic sandstone with lots and lots of dinosaur tracks in it. There's a good example of what wind ripple deposits look like. This was an avalanche. Okay, there's a gopher story to tell as well. Probably the most abundant mammal in the sand hills. Is it a 200 million or is it a billion of them that live there? Does this look familiar to you? This is where they've excavated their tunnels and brought the sand to the surface, made them out. Now that I know about them, I see them everywhere. I walk into campus some days, and there's some new gopher diggings over there to the left. So Becky worked on this. This was part of her PhD, and so the key thing here is these upward slanting tunnels. So this guy is excavating, and this guy is piling that stuff up on the surface so that we can have open tunnels, not just temporary things where you keep going in one direction and never come back. Here is the best place we saw these, and that so this looks a little odd. This is a well-developed, at least for the sand hills, it's a very well-developed soil. It's here because a lot of plants grew on the surface, and their roots added organic contact and coloration to what was originally this stuff. And so this is a break. This was a long period of soil formation, and then it was buried by dune sand. Okay, what's all this? These white things are the fills of things like this. And the story here, I wouldn't have thought I'm interested in how gophers live after volcanoes, but here are gophers maybe a few months after the eruption at Mount St. Helens. There's still snow present. There's the soil. There's the snow. Here is the blast deposits. And here are the gophers that were here all along. They were going to make it through the winter under the snowpack. Then they get this, but they're still digging and piling the stuff up high. And so this movement of the sand, cutting into this, and then you can see, so this, he's heaping up the sand here, but eventually they're going to want to build this further, and they're going to use this for they're going to backfill this, stuff it with sand from down here. That's what these are. You didn't take the reading here, I'm guessing. Here is the sequence. 1,000 years ago, there was lots of grass and soil formation. There was a drought. The dunes started to move. They started coming down here, and here are the remains of those gopher efforts. Okay, that was 800 to 700 years ago. What else was going on in the Western United States? The Cliff House here, this is one of many ancestral Pueblo sites. And so that was about 700 years ago. That's about the time that the people abandoned this part of the world and went to places that had more rainfall. Here, this is in Eastern California, southeastern California. This lake is about 5 miles across now, but we know now that there were 2 low stands of this thing. It doesn't have an exit. It is a closed basin. And there were 2 low stands, one 840 years ago, one 600 years ago. So that ties into the Nebraska story pretty well. It wasn't just in Nebraska, it was just in California. Okay, and Africa is loaded with deserts, and those deserts, there's rocks that are being buried by the sand, and all those rocks, you get all these amazing, all this rock art. And this is telling a story of the same type with the gophers and the bisons. So the deserts haven't always been deserts. People lived out here, probably large populations of people were living in the Sahara, living down in Namibia. And they were artistic. And so they drew some of these. That's good evidence. All right, a little bit about the lakes and the marshes. So high water table, all the water that flows stays here and goes down. Here we are taking cores from Crescent Lake. Some of you know where that is. That's a good bird watching place north of Oshkosh. Push the aluminum tube down and pull it back up. Kind of crude, but we got some pretty good cores from there. This is a AmeriCorps outfit. You've got a larger aluminum tube, and you've got one of those vibrators that you might see at construction sites where they want the cement to go out. They vibrate it and get it to flow. Well, you can attach that to at the top of the pipe, get it up here and started humming, and it just keeps going down. And so here's the aluminum tube, and here it's been, we sawed it in half lengthwise. And so 5 feet of this black muck in the marsh, and then maybe 1.5 foot of sand that's overlying more of the black muck. So what happened here. It looks like you had a really good marsh going for quite a while. And then you had activity on the dunes and they spread sand over the marsh. And then the rain came back and the muck grew again. All right. Battles on the plains, rivers versus dunes. So I told you about how the loess can easily jump over a river, but the sand can't. And there is this boundary between the sand hills and the loess, and moving the light right along the boundary. And I think that's probably the result of a river that flowed out this way instead of this way. So there's lots of time, and much of the dune field is bordered by a river here as well as here. All right. So this was an exciting day when we realized we had the tracks of the animals, and maybe a bigger surprise was we found the dune dam. So what is this? So Oshkosh is down this way. Here's Blue Creek, beautiful stream, perennial stream, trout in it. And where does it come from? It comes from right there. And this is all dunes right here. There's a little smaller tributary to it here. And Alliance is 30 miles away. Right near the airport at Alliance, you can see there's lots of dry gullies and just dry streams that flood in the springtime. And so that's 30 miles away. And we came to realize that this is a blockage. The rain diminished, back at a certain time. The dunes were able to cut off the rivers. And when the water comes back, these are ponded. So Minnesota's got about 10,000 lakes. There's close to 1,000 lakes upstream from this dam. And so this is the main plug up on the whole thing. So water is just pouring out of this spring. If you go out there, you drive up to Crescent, or that's uphill all the way. You're going up to the lake, and so water is pouring out of the base of the dam. And so we did coring, and this is our final conclusion that this was where several different drainages came together, and this probably happened in a lot of places. We didn't follow up to find more of them, but there's one pretty near just west of North Platte. So here's the cross section. We think the dune is the canyon was cut like this, and this is all the fill. Here is some material that we could date. It was wood, and it came back at 3,200 years ago. So so the stream was flowing through here 3,200 years ago and was blocked soon after. All right. So very few dunes north of the Platte River. This is the same story that I was telling you. The sand is here, but for some reason it stopped moving to the south, and for some reason a lot of silt, and only silt, was deposited a landscape there. This is Namibia. That's the coolest place I've ever been. I mean, in terms of exciting and new, seeing new things. And this is a big dune field. And these are rivers coming in from the mountains over here. And 1, 2, 3 of them die out, but the Nebraska River is the northern margin of this giant dune field, which is moving this way. This is a different kind of dune. It's not a transverse dune. It's a elongate dune, elongate with the wind direction, but it's not going past the Nebraska. There's enough floods on the Nebraska to trim it off year after year after year. And so this battle between the dunes of the rivers is widespread in Africa, here, and then also in the Sahara. So salt, I think, is what killed these trees. But it's an amazing place. Dunes as big as those in the Sand Hills, but no bigger. Okay. What about you're wondering, how do we know how long these sand grains been in the dark? So here's Ron Goebel. This is Ron Goebel. Typically, you can't get a photo of him because he works in a dark lab. And here he is squinting in the sun. And he's driven an aluminum tube into the sand, and he will pull it out, get another plug on the other end, and take it back to the dark lab. Okay, so how long has that sand been in the dark? So this optically stimulated luminescence, I can't give you much detail, but he's got a good setup where you can hit the thing with a burst of energy and it will give off the energy that it was storing. And how much energy was that? And you can calculate the age. It sounds, do you believe that? But people were critical, especially the people who loved the carbon-14 life. But it turned out this was, I think it was first carried out in the UK, and it has caught on, and yeah, nobody's critical of it. But so here are those really young, the 800, 700 year dates I was talking about. So, and the white is the windblown sand, and the black is the loess. And there's pretty good correspondence. When there was dune movement, there was loess deposition here and here, here and here. So that's kind of a state of the art. So at that site with the gopher stuff, 1860 years before present here. So that was a well-developed soil. It was buried, and a lot of the sand came back at about 800 years ago, and sand up here 150. All right, and what causes the climate changes? Our hypothesis, we wrote a paper that got accepted at Science, I still brag about that, as you might have noticed. And this was Becky Schmeisser's work as well. This was, there's all kinds of data available on how strong was the wind, how long did it last at Broken Bow, at North Platte. So that data is available. And so we asked the question, well, if there was a desert out there today, but the wind was the same as it is today, what kind of dunes would form? And some of it. Sorry. So these the transverse dunes, okay. We think, so these are winds out of the south down here, winds out of the north here. And so we think the modern dunes fit pretty well with the transverse dune field. But these other dunes that are oriented this way, all right, that might coincide with this situation. So I'm no meteorologist, but I know the Atlantic is out here and there's circulation like this, a lot of onshore winds at the Gulf of Mexico, and that's what brings Nebraska water in the summer, late summer. No, it's early as well. And so this was our best guess that this big structure changed and moved a little bit westward so that not much rain was coming with this wind, whereas wind coming out of the south is bringing a lot of water with it. Okay. And I think this is loess or something. Yeah. So this is thousands of years ago, 160,000 present, and this is from a Greenland ice core. Here is the Holocene, and that's the Holocene. We're living in a interglacial period. It's between glacial periods, and it's not over yet, and I ain't gonna be over anytime soon. Climate warming is going to perpetuate this, but things have been pretty stable here. But look at the amazing variation in the temperature of the atmosphere, and how do you get that number from an ice core? I'm not going to try to explain that. I could, of course. All right, but anyway, so the Ice Age was really an amazing time of climate variation, which to me, I mentioned climate change. Some people say, well, I don't believe in this climate change stuff because, climate is always changing. And so what? And to me, if we look at the Earth's climatic history and we see, oh, it's just moved all the way. It's really amazingly steady. Oh, well, there's nothing you can do to change it. I would accept that climate change is a bunch of crap. But suppose it shows all these amazing things, it's really sensitive to something. And a record like this, I think, goes a long way to understanding that, no, we're not the only thing that changes the climate. Something else has changed the climate in a big way. All right, this is, I don't know if you want to read that whole thing, but here I think the climate cycle was repeated and repeated and repeated in this dune field, and we just have a shot at learning about a small sector of that because the dunes cannibalize themselves as they migrate, so we don't have a long, steady record. All right, there we are, suffering in the field. Okay, do you have questions? No.
And then before we get into questions, I would like to take a moment to launch the survey and also distribute the surveys in person. We'll collect these on your way out, and we'll leave the survey open in the chat until all questions have been answered. I know we do have a couple online, and then we have a mic to bring around for those who have questions in person. Okay, we can start with some online questions. The first question is, are the sand hills in Nebraska what the early Spanish explorers called the Great American Desert?
Here I am, I know human history. I know less about it than anybody else. I think that's reasonable. But certainly the whole dune field wasn't active. It looked more like that Wyoming picture I had, I suspect. With there's dunes, but there's cattle in between the dunes eating. That's my guess, but it wasn't a full desert at that time, no.
Okay, and then we have another question. It says your track discussion or example brings up the discovery and appearance of human footprints briefly evident at White Sands National Park, being 20,000 years old, but continually disappearing. Is their dating strategy comparable? Comments?
Okay. Yeah, I don't know. I haven't looked in enough detail at that to give you a good answer. I guess from what I've heard from others, the USGS was doing a lot of that work, and I think it's pretty well trusted. But like any science, it's always open to change. But I guess I'm a believer at this point, but not because I know so much about it. It's just what I've heard makes sense.
The next question is, what is Aeolian sand?
All right, Aeolus was the Greek god of the wind. So Aeolian sands are windblown sands.
Okay. The next question is, there's a ghost forest of Great Sand Dunes National Park up against the Sangre de Cristo Range, similar to Namibia.
Think of where that is. Is it, you said in California?
It doesn't say. Oh, it says, this is a separate one. Ghost Forest of Great Sand Dunes National Park.
Oh, that's in Colorado. Yeah. And then the question
Is it similar?
to Namibia. Well, those are really big dunes there, and I would say that they may be as big as those in Namibia. They're a different type. They're from winds coming out of the west and getting to the mountains, and then having, they depart from the land's surface there. They're going up over the mountain. So they dump a lot of sand there. It's a one-way street. They can't keep migrating through the Rockies. So it heaps up there to make really tall dunes. But the area of dunes is not very large, really.
Okay. Near Cairo, Nebraska, is that Cairo, Nebraska, there is a huge ridge of sand. Can you talk about that? It seems out of place.
My lips are sealed. I don't know where that is. Cairo.
Cairo, Nebraska.
Oh,
West of Green Island.
Cairo. That's what.
Yeah,
Okay.
yeah.
All right. I read too. There's a huge ridge. I don't. No, I don't think it's. If it's parallel to some of the drainages, I believe that it is a dune. That's the only way I can think about it. There's some guys on East Campus now that have been interested in smaller dune ridges out in an area that's mostly loess but has some dune sand.
Okay, so the next question. The topic as shown spells the lecture. I guess they're just wanting to know why it's Sand Hills, two separate words, and not Sand Hills, one word.
People love to fuss about that. I'm not in Nebraska, I don't care. And actually, I used Sand Hills my whole career, and nobody gave me a hard time. So, but I've switched it over. I'm inflexible. And so, I think Sand Hills, one word has kind of got the momentum now. And if you need to fight back, but I think it's gonna be a tough one.
Okay, the next one is how many rivers cross the area where the sand hills are located in order for the sand to cover this much area?
Well, those aren't the rivers that delivered the sand. And so counting, you got the Dismal, you got the North Platte, the North Loop, you got the Middle Loop. So they don't, their presence doesn't give you ideas about how the dune field grew, I don't think. But it does, it's, I think, very interesting in terms of the hydrology. And so I would say that eventually the sandhills are going to be swept away by rivers. And is it going to be those rivers? I think you need input from the Rockies to really get that done. And maybe glaciation in the Rockies, more glaciation. But yeah, that's it.
Okay, did the Platte River flow into Hudson Bay, Canada years ago?
I know the Missouri River did. And I think it's quite possible, but I don't know for sure about that. But yeah, there's good literature now, got a lot of good studies about how a lot of the drainage went northward and not to the Gulf of Mexico, but I don't know where the cutoff is. I guess if the Missouri River, it would have to go. Yeah, so I think so.
How do cedar trees moving into the sand hills change the soils and hydrology?
They're changing the ecological system. I don't know how much they'll affect the dune field is now stabilized. I don't think they're gonna bring about destabilization. But the birds that used to be strictly in the sand hills without any cedar trees, maybe things are gonna change for them and other birds are gonna be coming westward and so I'm no ecologist.
What causes the buried sand grains to build up energy over time, not just being in the dark, right?
No, they build it up by just, yes, sorry, it is from being in the dark. It's everything. You can't get away from radiation on this planet. We've got it coming into this auditorium right now. And down in the soil, there's minerals that are breaking down and sending out radiation. So it's a tiny, tiny amount of it, but if there's a long time, that can become measurable.
What is known about the interaction of groundwater and surface water inputs to the wetlands of the sandhills? Does the relationship typically change over the course of a year?
don't trust me. So I said geologic history. I didn't say that, but no, I don't know about it. You know, what I do know is, you know, there was a lot of draining of the marshes, and I think that has come to a stop. That was an obvious big deal that needed to be stopped, but I don't know. Certainly surface water could well be pretty heavily affected by lots of processes. Not like there's a big human population out there.
I think this is in response to the graph that you were showing. But is it correct that climate change is happening faster than it would naturally due to human activity? I guess more about that slide that you said you don't
Yeah,
really
yeah,
know.
Yeah. Is it correct that climate change is happening faster than it would naturally? Well, I mean, so yeah, those are really rapid, and that's an example of rapid climate change as done by glaciers. There's many other ways that volcanic eruption can change the climate rapidly, and a series of them. And some of the big extinction events are, well, actually, I think 4 out of the 5 are due to volcanic eruptions, and the atmosphere becomes a bad atmosphere globally there. So, all right, and you want to know?
The next one, I submitted a question online previous to the presentation regarding a large flood from a Sandhills dam that changed the direction of the current Platte River around Fremont area.
Well, it wasn't it was a man-made a dam that was a Sand Hills dam. Now, what does that mean? I don't know. And I think I would have heard about it if it was a natural event.
That changed the direction of the current Platte River around Fremont.
Well, no, that can happen. You know, big events. There's lots of ways to cause floods, but I don't know I would think it would have to be a pretty big reservoir.
And this person is still asking about that graphic that you showed. But maybe Claudia, if you could be more specific on.
Well, all right. This is, I said, my take on things. If you just back away, I know some geologists who work for petroleum companies, and one of them said, we had an argument at a campsite, and the next morning he said to me, I've been thinking, and do you know what ETM or something like that? It's oh yeah, I know what ETM is. That was a thermal maximum. The TPM, yeah, that was 50 million years ago, and yeah, that was really a big change. And then he says, "Did we cause that?" I said, "Are you kidding? 50 million years ago?" He says, "Gotcha." So something happened. A rapid change of temperature happened, and humans didn't cause it. That means we couldn't possibly change the climate of the planet. Really? How does that say anything about what humans are doing to the planet? And like I said, if you looked at geologic time and saw, whoa, it's always been spinning and not tilting or anything, but it's the the climate in Nebraska has been the same for 1 billion years, probably. I would say to that, wow, if that's right, I'm not worried about climate change because this is a planet that is hard to break, hard to change. So,
So talking about the Cairo, Nebraska, with the huge ridge of sand, she was just clarifying that it's on the south side of the South Loop River, so it shouldn't be there.
well, if it's Aeolian, if it's wind blown, yeah, that would be hard to explain. But yeah, you know, there was a master's degree from East Campus, and you could find out about that if you ask some people in that area. But sorry, I don't know, but it is possible that it's windblown, and so I know that they're there. I haven't been out there and I haven't seen them, but there's probably more than one.
Why do sand hills have grass prairie when other sand formations do not sustain much vegetation at all? For example, the Southwest Dunes, like Great Sand Dunes, National Park in Colorado, White Sands in New Mexico, Coral Pink Dunes in Utah.
Well, the plants just can't get established. And so what do you need? You need seeds, you need water. And you don't want to be burying everything in sand while the plants are getting started. There's some places that are just so harsh, and the gypsum dunes in New Mexico, that's not a real easy place to grow plants. I wouldn't want to try to grow tomatoes there. There's lots of reasons that you can have, but they're all small scale. And so what I said was that beaches and deserts, that's where these big accumulations of dunes form. And those places are unique in their own ways, and I don't think so that's a closed basin that's very saline, and so that's pretty hard on plants. I guess that would be part of it for the New Mexico.
Okay, and then this is the last online question, and then we'll take questions from the audience. There is evidence of an ancient riverbed that flowed almost due south-north of Wahoo that seemed to connect to the Platte River. The person seemed to say it was a giant flood from the ancient sand hills that caused the change in direction of the river. The river didn't flow north. The area is north of Wahoo.
Yeah, I know the place that you're talking about, and I haven't heard that. And I'm skeptical that it would come from the sand hills. Those are small streams, and yeah, I don't know, but yeah, there was a guy. He's now retired, and haven't seen him for a long time. Who was very interested in that particular place, but no, I'm sorry, I don't know.
All right, and then we can go to questions from the audience. If anyone has anything, we have a mic we'll bring over.
In the Ogallala rural area, I mean, there's a lot of sand hills to the north. And then I imagine the river was maybe the cause of it stopping there then. But there's also a little bit of sand hill area over by Grant. And then I was wondering how that, because there's no river over there.
Right.
But then there's a lot of plains to the southwest of Ogallala, like south of Rural. That is extremely sandy, but it's extremely flat.
Mhm.
So I wanted some comment on that.
See, I don't know the geography that well. You can have sand on a flat surface, if you've got shallow flooding by water. But one little flood at a time, you can get it, and there's maybe not enough wind to mobilize that. But, yeah, I don't know. I'm not gonna claim I do know. And the second part that you said, there's,
Well, south of Rural.
south of Google.
It's called the South Table up there, and it's very sandy soil. But it's just flat, it's like Kansas.
Well, see that those formations around there, they're relatively young, they're not very well cemented, and they weather into a lot of sand, so there is a lot of sand available, and I guess there may well be some places where there's enough wind and for some reason, no plants to hold it in place. But, yeah, you wouldn't have to bring that sand in from very far away. There's a lot of local sand weathering out of those. What are they? Oligocene formations.
So you have the sand hills over here, then there's a valley, Flat River Valley, and there's plains there. It just, the plains aren't blowing over there. So
Yeah.
just because there's enough dirt or, and yet over by Grant, there's a whole bunch of, some dunes, well, not a whole bunch, there's a few dunes, so.
Yeah. I think maybe that was some of my statements were perhaps overstatements in that this explains every dune that you'll ever see. That it's gotta be a beach, it's gotta be a desert. But those are the places that I would say 95% or more. And I think there are places that are kind of unique. And, why is it that plants aren't growing there? Well, the bedrock is right near the surface, so they can't get their roots in, or there's all these possibilities. But yes, plants really are a major control on where dunes can form. Major. It brings the question of what about in the Precambrian, way before the evolution of land plants? What was the planet like then? Yeah, so everywhere was dunes, and there's nothing that has shown that that's true. All these Precambrian rocks are Aeolian sandstones. That's not the case, but anyway, yeah, plants play a big role, and there's lots, I guess, a lot of different ways to have a virtually plantless surface.
I have two questions. So one with the eastern red cedar, I think in the Flint Hills of Kansas, the concern is that the bedrock is so shallow that they actually punch through the bedrock and it changes hydrology of the landscape. What is the bedrock really deep in the sand hills? Is there, eastern red cedar would be like 6 to 10 feet would be the max, root depth.
Yeah, that's common, and so how much sand is out there, you might think, oh, it just looks like the surface, not very far at all. So, yeah, I think the trees that you see do probably have the roots down.
Okay. And then my second question is, given the possibility of climate change and weather variability. Is there a possibility that the sand hills could become mobile dunes again if we experienced like a large drought?
I know a guy who wrote a novel about that. And, yeah, I think so. I mean, it's possible, but, you know, there's also, I mean, there's lots of novels written about what New York is gonna be like in 100 years or whatever. So, yeah. And it was the sand hills didn't mobilize well. That means probably a tough time, you know, but, you know, the Ogallala aquifer isn't gonna go away just like that. So I would say people will try to maintain their farms, even though rainfall has stopped, and they'll take all the up the aquifer to that.
Any other questions? All right, well, thank you so much, Dr. Loope, for sharing your time and expertise with us today. Thank you for the Nebraska History Museum for hosting this event, and thanks for everyone who joined in person and online. Have a great rest of your day.